before he will tell us the story about quantum computing. George received his PhD in particle physics from MIT in 1970. However, when he joined the Lawrence Berkeley National Laboratory and also the UC Berkeley, then he decided to switch to cosmology, working with Professor Alvarez. And since then, he has been working in cosmology. Now, the important mark he has made naturally is receiving the Nobel Prize in physics in 2006 for the discovery of the anisotropy of the cosmic microwave background radiation. Besides the Nobel Prize, Professor Smoot also received a lot of awards. For instance, he received the Lawrence Award from the U.S. Department of Energy, the Einstein Medal from Albert Einstein Society, and also exceptional scientific achievement medal from NASA because his toy was launched by NASA to make the discovery. Now, in addition, George has a very remarkable contribution in educating the science to the public, and as a result, he also received the first medal in 2009. Now, besides all these awards, Professor Smoot also has a lot of honors. So, for instance, he is the member of the U.S. National Academy of Sciences, and also he is a fellow of the American Physical Society. So please join me to welcome Professor Smoot.
So thank all of you guys who braved the rainstorm to come out. I'm going to give you a talk which I made the second half to be provocative or strange or some combination thereof, and the first half to impress you guys with how much progress we're still making in cosmology, even at the present day. New data are coming in quite a lot. All right, so let's get started. The first half should be pretty comfortable for you. The second half should be a little unusual. If you're thinking, I'm going to tell you about how quantum computing calculations have revolutionized cosmology, I'm here to knock that down. We're in, if you know the hype phases for technology, we're in the beginning hype phase before the huge disillusionment, before the common realization. We're still way down here at the beginning for quantum computing, particularly for cosmology. Although you can say great stuff, like with quantum computing, in principle, we can run some really complicated simulations with a lot of variables and with quantum mechanics involved in it, and maybe learn something new about the universe that we wouldn't have learned with our classical calculations. And there are a few papers out. There is a nice paper by this first group, started by Alexander Kaufman et al., that is talking about quantum computers for the early universe and what kind of computations to do and so forth. But it's talk. There's not too much results. There's an interesting paper on cosmological simulation of the dark matter made on quantum computers. Again, I'll show you some stuff from the first author. His simulations with classical computers are much better, but it's still a start. And there was big news a couple of weeks ago that a team led by Maria Spiropoulou had showed that they could send information through a wormhole by making a quantum computer that was a wormhole, and that's indicated down here. It's supposed to be a 7-element, and they propagated a piece of information through here to the other side. Now, this is a big deal if you're talking about Einstein-Rosen wormholes, because they usually are supposed to collapse before any information gets through. But these guys claim they sent some information through, and they were using the Google computer instead of the IBM Continuum. But turns out there's a lot of controversy on it. If you read the news since then in finer detail, there are lots of people who are arguing they didn't make the right kind of wormhole and whatever. You can actually make wormholes where you can transmit information through in principle. If you have big rings of negative energy, you can overcome this problem. So there's a lot of dispute. There's not so much exciting new results. So I'm not going to talk about that much, except on the bottom right, something else that made the news recently, which was some condensed matter people decided they'd simulate a black hole and 2 dimensions and try and look at the boundary. And they surprisingly saw the boundary was glowing like crazy. That's that light. This isn't the kind of stuff that people are working on here. That's, Hu was doing calculations on using the spin of a black hole to do super radiance and so forth. Is one of the things you'd expect, but this is not, this is a surprise. So far, quantum calculations are pretty much all promise. Their real results in quantum computing for cosmology are actually pretty thin. That's a big issue. We're actually making bigger strides forward using AI, but that's an even more complicated kind of question. So I want to talk about stuff that's a little different than that, where we know what we're doing. But first I'm giving you a quantum computing quiz, which is going to come back to get you towards the end of the talk, in the second half, in the middle of the second half. Okay, so the first question is, what is the quantum no-cloning theorem? Okay, so this is big and deal. Yeah. Because of this and related lemmas, the Chinese government is investing billions of USA dollars on this technology. Okay, why are they doing that? Right? And how does the no-cloning theorem prove that human teleportation is impossible? Okay, this is on a quiz. You guys, if you get 3 out of 4, it's a pretty good score. Okay. Now, how do we get around this no-cloning theorem for quantum computing? This is a big issue for quantum computing. In conventional computing, we just take the original data, run the calculation for a while, stop, read out everything, a perfect copy of everything, and then run it again if the computation fails, the computers fail, something happens. And sometimes you run it twice just in case there was an error along the way. But the fact is you do what's called checkpointing. This is something you can't do in quantum computing. Okay? And how does this show that the universe is really a quantum computer? That's the second half where the bad things come to greet you. All right, so what's been the real progress in cosmology? Well, the real progress in cosmology has come from the fact that we have been driving, the cosmologists have been driving high power computing for a very long time because it plays such a crucial role. Because if you think about the universe, it's a big thing to simulate. It's a big thing to analyze, it's a big thing to calculate. So there are 3 areas where I can point to that high power computing is very important to cosmology. The first is analyzing the observational data. At the beginning, when I was young, we didn't have much observational data. We measured it in megabytes, if we were lucky. Then it got to be gigabytes, now it's like exabyte a night. It's a huge amount of data coming in, and a huge amount of processing that has to go on. And this data is being collected from telescopes on Iron Mountain with very big throughputs, 4 meters and greater, from satellites, and a lot of other places like that. And so being able to process really large amounts of data and categorize it and show, and I'll give you some examples of large amounts of data and you'll understand that. It gives you an idea of the scale of the kind of things you have to do. The second thing that computers have been used for, and this is truly a challenge for these computers, is to simulate the evolution of the universe. I'm going to show you examples of simulations that start near time equals 0 and go on for 14 billion years and covering ranges in the sky that are many billions of light years on the side. So those are really substantial calculations, and they're not simple because the force that we're using to describe that is gravity, and gravity is a long-range force. So you can't ignore the effect of this particle on the part of this one over here, the way you can in some places where it's only the neighbors that matter, right? And then, in order to test our cosmological models, we use high-power computing to refine the theoretical models and run the more simulations and so forth, and then compare the observations to the simulations. and do a lot of calculations. And these are really substantial sort of calculations. And so for more than 2 decades, cosmology has been driving the development of computers. We did some of in the early days, the people who were doing computers, they were solving eigenvalue problems. They want the 1 or 2 biggest eigenvalues, and that was it. Eventually, we were doing 10 million by 10 million matrices, and we wanted all the eigenvalues and the cross-link. We wanted the whole inverse data in order to be able to figure out the links, in order to be able to make a comparison between the observations and the theoretical, because the observations had some cross-links between the two. So that's really quite an amazing thing. So the picture on the right, with a little bit of flaky colors in it, is a 10 million pixel map. That's from the Planck satellite. In the good old days, we started with 6,144 pixel maps when we made the first map of the sky. That was a big challenge for me in those days, but nowadays 10 million pixels is within reason for what we can do. That's 10 million pixels. That's reducing many, many order of magnitude more data in order to get it to this map, the matrix equations that tell you the links of the errors between it. But we can reduce those to basically 6 numbers, right? We make a relatively simple model of the universe called lambda CDM, or dark energy, whole dark matter, and we can put all the data together, and we only need 6 parameters, and we measure those parameters with pretty exquisite accuracy. So one of them is the physical density of baryons, that is, the stuff that's in this room. Everything in this room is a baryon or electron. So, the physical density of that is on the order of 2% of the matter, the energy matter in the universe. And we know that, you see, with incredible accuracy. How do we know that? Well, we know it because we can see what kind of fluctuations should cause in the microwave background, and we fit to the data, and with only 6 things, you can determine that with fairly good data. The next thing is the density of dark matter, right? And that's running around 12% of the energy density of the universe. And it's also got a pretty small error bar. And this one, unfortunately, for this slide that I picked, it only tells you something about a critical angle, but it has to do with what is the basic sound horizon size or the light horizon size at the time of last scattering. But then there's also the temperature of the universe, the tilt in the power spectrum. We see fluctuations on every scale. It's almost scale invariant. If this number was 1, it would be completely scale invariant. It's slightly tilted to be less than 1. That is, as the universe is expanding, it is slowly having less variations that come out into being. And then there's a thing called sigma 8, which is unfortunately, a lot of astronomers are involved in this. It's the fluctuations on an 8 megaparsec scale, because an astronomer said 8 megaparsecs is roughly the size in which the material from a galaxy should come, and I should look to see how big a fluctuation that should be. And that's a number, and that's one of the things that actually is a controversy. But we have incredibly good measurements for fitting this model, but we're assuming a model, and we're fitting all these data, these 10 million pixels, we're fitting these limited amount of parameters. The lambda CDM, the cold dark matter, and this is the sort of wimpy cold dark matter, really describes observations very well. So plotted across here is a mass scale from 10 to the 12th solar masses up to 10 to the 23. And plotted up here is the size of the fluctuation, the fluctuation of the mass divided by the mean mass. And you can see there's a dashed line in there, which is the prediction of lambda CDM. It actually basically a power law, but I think of it as the small scales. On the large scales is the power law. And in between, there are tiny wiggles. And the details of those tiny wiggles are not important here, but they're the baryon acoustic oscillations. And they're very small effects, but they're the fact that there is interplay between the photons and the baryons plus electrons in the early universe, and you get these oscillations. And what you see is the data are falling on this curve, and it's basically scale-free and scale-free, except for a little scale in the middle. And that little scale is set by basically sound speeds in the universe. So here I'm showing you an example of a simulation. How do we compare? So let me start this over again. You see the universe is expanding, and it expands up to a certain point, But if this is an overdensity that's going to form a galaxy, it starts collapsing back down. It goes up to the 8 megaparsecs and then it starts going down. That's h squared for the expansion rate. And then what you see is the simulation runs, and it runs. Now we're 9 billion years, 10 billion years. So it runs for a long time. And what you see is you can see the outline of the galaxy, but you also see the galaxy has a lot of substructure. There's a lot of sub-halos inside the galaxy. And in fact, it says up there, it falls down, it's almost the second power of the mass per decade. This is the thing that we'll come back to later. This is the prediction, as I was showing you, things are scale free. This prediction is a prediction that is very good in one way, but very bad, at least to one of our controversies that we have today. Now I'm going to show you something that was released fairly recently, although it had predecessors. This is the largest computer simulation probably ever made, but it's certainly the largest cosmological simulation ever made. You look at the scale, that's 3 billion light years, so it's nearly 10 billion light years across. And you can see there's part that's gas, there's a part that is made of dark matter. You can see which part's dark matter. You can see where X-ray emission is coming. Now, only in densest areas where the gas is hot and compressed, you actually see X-rays. But this simulation is a huge simulation if you realize how many particles are in it and how long the calculation had to go on. Let me show you how the simulation looks. The main picture is gas, and the lower picture is the details of the dark matter. So you can see what's happening when one of the galaxies is forming. And this just goes on for a long time, right? You're gonna run this simulation, it's a big complication. Here, where these simulations are usually done on great big server farms, basically. It's the kind of thing you would expect. In the early days, I used part of my grants to help buy some computer servers, and some other people in higher physics and others, and we have a server. And then eventually we got a big computer to do that. And now there are even bigger computers you can rent online to do this. But you can see what's going on. It runs and lots of things happen. Right? It's still happening a long time. It takes a long time to get down to this point where we think we're at the present time. So I can show you a scan of the present time, which was done by the predecessor calculation. This is a thing which now is 3 billion light years across this MPAR. And this is the sort of the framework of material. Their filaments go between regions that are galaxies or clusters of galaxies. Because you started out with a very uniform environment, and it's slowly fragmented and collapsed and pulled together. And so these guys, of course, are zooming in on one of the biggest set of filaments that come together, because that's one of the biggest things. And you say, how often when I look out in the universe should I see something this big? And that's one of the questions that comes to their mind. It also is a lesson to us that we don't live downtown. The difference between us and Andromeda is like between two of those close dots there. I guess I should try and use the pointer. It's like between this guy and this guy. If we lived here, we looked out in the sky, we'd see galaxies everywhere. But now we're going to zoom back out, and you're going to see, on a small scale, it's very complicated and very wrought up. But on the large scale, it's pretty uniform. You know, if you're driving around through the universe, that looks like a pretty uniform system. So here is data that was released less than 2 weeks ago. This is from the Dark Energy Spectroscopic Survey Instrument, DAISY for short. It's released its first year of data. This is a wedge of galaxies out to a redshift of about 2, out to when the universe was roughly half the size, or a third the size it is today. Out here is what we call the Lyman alpha forest. If you have quasars out here, and there's gas and dust in between, you will see absorption lines, and you can measure along those lines of sight and see the absorption lines. So the stuff that's relevant is this map of galaxies and this map of the dust and gas in the early universe. So this is just to give you some perspective. That's the Nobel telescope at Kitt Peak. That's the slice of the galaxies that we're seeing, cosmic microwave behind, and left off the dark quasar Lyman alpha forest. So DAISY, it's a 5-year effort. It just released its first year data, that's what we're seeing here. It has 3 years in the can now. And a week after this happened, at the telescope, the thing that holds the 5,000 fibers broke and fell down. Fortunately, it did not injure the fibers, but it stopped them taking concentration, so they had to stop now and rebuild and redesign that structure and get back into business again. But the goal here is at the end of 5 years to have 40 million galaxies measured. And right now they're on the scale of 400,000 quasars. And you want to measure them, get a good picture of them, but also measure their spectrum very precisely. And that's done by these 5,000 fiber optics cables that are then have robotic positioners that place them on in the focal plane where the galaxy is, and then that fiber takes the stuff down to one of the 500 spectrographs, and it scans that. Well, each spectrograph does 100, so it's a little more complicated. Already, they have 5.7 million galaxies in their map. I'll show you the map in a second, then I'll show you the grid. And this is going to, when it comes out the second year, be the biggest sky survey to date in terms of knowing what's going on. So here is a rotating wedge, but this shows you every one of those things is a galaxy, right? It's not a star or whatever, it's a galaxy. And there's roughly 1 million of them in here out of the 5 million, because it's just a wedge out of the cap that they're looking at. This is a map from the Cosmological sky survey, which up till now was the biggest one. And now what you can see is a fly-through of that cap. And here you're going through a large galaxy cluster and out in a place where there are fewer galaxies. But what I want you to bear in mind is, look how many galaxies there are out in a small section of space. This is not the whole universe, the observable universe. This is just relatively nearby. The Cosmological sky survey doesn't go out quite as far as DAISY does. Interesting to see how big a data set this is. Here's over 1 million galaxies. It's got a postage stamp of each galaxy. With DAISY, it will also have a high resolution spectrograph with it. And so we're seeing the universe on a fairly substantial scale. This is data that's released. They didn't make a very fancy version of this. But next year it'll be twice as big, and it'll be bigger than the one that I was showing you, the fly-through that I got from Big Al. And it has a lot of additional information. And already there's speculation about what it's telling us about, does dark energy stay constant with time, or is it changing? And some of the people in the team are speculating there's been some change in the dark energy content. It's not lambda CDM, it's some other energy form. Well, it'll be interesting if that's true, but it's something to see. Okay, so remember this simulation that we saw at the beginning with the galaxy that formed, and it's got all these subhalos. And then over here is the real galaxy. This is our galaxy, the Milky Way. And here are the known small galaxies, dwarf galaxies, that are around us. Now, it shows you how old I am. When I started, there were only about 6 of these. Now there's 24 or something. According to cold dark matter, WIMP kind of dark matter, this should be around 1,000. So what's going on? Yeah, they never blamed the simulations, not until later. So the solution to the dwarf galaxy problem, that is, we don't see enough real dwarf galaxies compared to the simulation, well, you can blame the astrophysics. You can say, when you start forming the stars, they blow out the material, and somehow they heat the cold dark matter so it's not so cold anymore, and they prevent as many subhalos from forming. Or you can say it's not cold dark matter, it's not WIMPs, it's something else. So one of the first things that people went to was saying, all right, let's make some very light or warm matter. That is, it's light enough mass that when it's in orbit, it's actually hot and can escape, has escape velocities, can escape from the galaxy. And when you do that, the scale invariance, n equals 1, rolls over for cold dark matter, because this is astronomers, they do it in density and so forth. And so if you did it in curvature, the curvature would be flat, there would be variations in curvature of space-time, and then it rolls off because the stuff gets dissipated. Right? When you get out to something on very fine scales, the potential gets distributed and gets pulled apart by the Copernicus calculations, by the other activities. But if you put lighter things in, they have kinetic energy to escape, and the lighter they are, the more easily they escape, and therefore they cut off. And so here's one megaparsec scale, 10 megaparsec scale. That is 1 megaparsec, so that's roughly the scale of our galaxy. And so if you put some more dark matter in, then you're going to make it so you don't form nearly as many subhalos, and you could explain it. Now the problem with that comes up other ways, right? So there's the simulations with WIMP-like dark matter or heavy dark matter, and the lighter dark matter. Now the line alpha Pharos I mentioned, where you see quasars, which are the first galaxies turning on, and their black holes are gobbling in material and they're radiating like crazy, you get a very bright signal, and you can look at the gas and look to see what kind of signal you see. And here is a plot from 2013 of what you see, what you predict for warm dark matter with a light 1 keV and 2 keV, and then lambda CDM. And what you see is there's a lot of the high frequency power. You notice how much power there is here in green, how much extra signals there are here in green at high frequency. You just don't see it there. Now, the early results from doing these kind of surveys seem to show there is some high frequency power. Now the question is, why is that? Is there something funny going on? Or is it really telling us that it isn't, warm dark matter escaping, that there's some structure or stuff going on, but then it gets blown away by some other kind of thing? We also here, with some of our colleagues, been speculating about whether the dark matter might be quantum mechanical. That is, rather than being small, particles like protons or heavier, or neutrinos at the keV range, what if they are some extraordinarily light particle? And of course, everybody's favorite these days is the axion. And if you have the right kind, if there are bosons, you can have Bose-Einstein condensates whose characteristic wavelength, Compton wavelength, or particularly the de Broglie wavelength, is on the scale of megaparsecs. And it's on the scale of the center of our galaxy. And then you will get some kind of structure. You can reinterpret the cold dark matter as a Bose-Einstein condensate. It will behave like it was a cold particle, except it has local pressure due to the de Broglie wavelength and so on. And so here's a simulation, and you can see the Bose-Einstein major part of the condensate, but you will also have part of the condensate that's at slightly higher state. That is, you can have L equals 2, 3, 5, 100, whatever it is, out there. Plus you have Compton wavelengths across here. You can see various kinds of structures. So that you can see that there would be a Bose-Einstein core, a condensate core, and then a collapse system around that. So this is interesting because this tells you quantum mechanics could operate on a scale you've hitherto thought quantum mechanics didn't have anything to do with, something that's much larger than the solar system, much larger. It's a big fraction of the center of the galaxy. So here is the simulation of what that would look like. And you can see it oscillating around. You see the center part of the condensate, but you see the same bosons are in the same wave function. They get excited all the way out. And they can be at different L values and be orbiting around the center of the galaxy. And so this is an interesting kind of activity. However, it's not clear whether it's relevant or not. And you can compare the WIMPs and the wave dark matter simulations. So over here, along the top there, you see cold dark matter, and here you see the wave dark matter. Here you see the wave dark matter again in terms of the gas, the cold dark matter, and the stars. And you see there's a big difference between what happens. This doesn't collapse down completely the way the WIMP cold dark matter does. It also has these extra waves caused by the quantum mechanical nature of what's going on, composed to the WIMPs, which are much more massive particles and therefore much less demonstrative of their quantum mechanical properties. So, and here's another simulation done one of our colleagues who was a grad student postdoc here and is now doing simulations otherwise, now with two axions whose mass ratio is a factor of 5. Now this turns out to be more complicated and more interesting because there's more degrees of freedom, but also because if you don't choose the right mix and the right max, there are instabilities. You could look at the possible solutions for making galaxies and more galaxies, and some are allowed, some are not. The heavy axion sometimes dominates, and the light axion sometimes dominates, and they make it unstable. But if you follow the right range, then they kind of come out okay. What are our solutions to the dwarf galaxy problem? Well, you blame the astrophysics. Must be the star forming and everything else pretty much. Or you can blame the cold dark matter, or you can blame the observations. So far they haven't blamed the simulations, but it'll take a while, but somebody will get around to that eventually. The question is, are the observations really proving things are that lumpy, or are they not? Who knows? One of the new tools that's not that new, I mean, it's ever since relativity was gone, we knew that there was a potential for gravitational lensing, but it wasn't until much more recently do we actually have examples of gravitational lensing, and even more recently do we now are able to make observations and standard observations in order to use gravitational lensing as a probe with what's going on. If you have a galaxy cluster and you have a faraway source and you're on the other side, you're looking, you can try and see the faraway source magnified or through the tubular cracks, and you can measure the potential of what's going on in the galaxy cluster or the potential of whatever is doing the lensing, and you can see what's going on. And it could be sensitive to what's in the subhalo of the core galaxy. And this is a way to probe and try and find out what that kind of matter is. So here's an example of a lens system that nominally you have 5, but one in the middle gets blocked, where there's an A and a B and a C and a D, and you see what they expected on models of what's going on and what was actually observed, and say, well, why is that? Why isn't the ratio of the brightnesses the way the positions are pretty close to where we want, but the ratio of the brightnesses aren't what we think they should be? Well, picking it carefully, but when people go through and analyze these very carefully, what they found is the flux ratios vary around about 2 or 3% more than they should. And so what causes that? Is there some substructure in the simulations or some substructure in the actual galaxies that's causing these different effects? And so one of my colleagues is here, up in the middle rows, I think, is the lead author on this paper. This is the kind of a caustic you would expect. I got these slides in the slightly wrong order. If you have a distant source, a galaxy or a cluster of galaxies over here, and you're in line, you can get a caustic, you can get what's called an Einstein ring, where there's equal distances around. If it was perfectly in line, you would get a perfect circle, and you would get something like this. And with cold dark matter, you expect this to be a very narrow kind of thing. But if you put in the wave dark matter that you put in there, you can get these different variations. Right? And you can try and say, I want to look for this. Well, it's actually hard to do. You need a very good detector because these are very small. If you look at the scale size, the things are in parsecs here, but it's quite a small distance. However, Alfred is our colleague working on this interesting galaxy. This is galaxy Abell 370, known as the Dragon. Well, so this is a cluster of galaxies with a few hundred galaxies in it. You will see there's a gravitational lens arc there, gravitational lens arc here, gravitational lens arc here, and one here. But there's a big one here called the Dragon. Okay, what's causing this? Why is it thicker? Why does it look like that? And that's what you see up in the top. Why does it look like that? Well, colleagues are working on it. They're coming out with a paper that's carefully being analyzing this, and they claim they find 36 new microlenses. That is, things that fall where this gap is, where this structure is, that microlens it and cause it to blossom up and so forth. We're waiting to see what's going to happen, but these data are just coming out. So here's the source moving around behind the lens. Suddenly you get to the point where you get the Einstein ring on the radio telescope, then measured it, and you see how well they measured it. It's one of the few things that actually the radio telescopes and the VLA, big radio telescopes, is big enough to be able to make a measurement of the lensing, like this Einstein ring, accurately enough that you can see with this kind of precision. But still, it's not quite enough resolution for the kind of thing that we need to do. Just the dwarf galaxy problem, there's a thing called the core cusp problem. That is, when you measure what you see in the way of number of stars or amount of mass and so forth, it kind of moves over like this as a function of radius. So here's the center of the galaxy cluster or galaxy you're looking at, and here's the prediction for dark matter alone. Most observations are showing that there's not enough in the center. Is that the question? Is it being blown out by some kind of gas physics that's going on when the stars are forming? Or is it like wave dark matter and therefore doesn't go down because of all the exclusion prevents it from getting down that way? So here is another way that people say, well, what if you heat up the CDM? Let's have starbursts. There's a big starburst, it blows a bunch of gas out, that heats the thing up and kicks stuff around, then it comes back down, and then it heats up again and does it over and over again. That can pump some of the cold dark matter out of the center. There's a lot of imagination, but there isn't anything so clear. So what we can say now is, we astrophysicists know much, and we understand some. Okay. We have plenty of evidence the universe conforms fairly well to the Landau CDM, but it's hardly definitive. It's hardly completely sure. And it's the only universe we got, so we want to actually tie this down very well. And in galaxy centers, the dark matter densities appear lower than expected. Something is either not letting them in or driving them out, so we don't know. So either it means there's some fundamental properties of the dark matter we don't understand, or there's something more complicated about galaxy formation than we expect. There is some evidence that the baryonic process is involved, but it's not enough to make us happy. There's no showstoppers for that CDM so far. But on the other hand, warm dark matter and other kind of things are not stopping us. It's gravitational lensing may be the thing that's going to let us make these separations. Here's a picture of the Milky Way. That the Milky Way is not like a proton. They're not identical sets of things. They're not like electrons are perfectly identical, or protons. They're not identical. They're very different. And they didn't form all at once. The galaxy formed over various times. So there's a bulge. It's a central bulge that we were looking at. There are galaxy clusters around the outside. There's a big disk. But we also have orbiting dwarf galaxies. And those orbiting dwarf galaxies have star trails coming out of them. That means they're actually orbiting through our galaxy. Some people worry about, well, what happens when we run into Andromeda? Is the solar system going to get kicked out? Well, we don't have to wait for Andromeda. We got plenty of these little galaxies shooting through us. So here is a beautiful of our galaxy with the star trails. And we've lived out about this far, so that guy was a good candidate for hitting us. Okay, so now I want to change gears and be more provocative. I want to talk about the holographic principle, and then I want to try and convince you that everything you see in the universe, all those 100 billion galaxies and so forth, are actually encoded in only 2 dimensions. Here's the first picture. You can buy this on Alibaba for $100 US.
Yeah, no, you too. Yeah.
That looks kind of 2-dimensional, but it's 3-dimensional too. Now that fish looks really good.
In Barcelona der vorstellbar gewesen früher und Corona war präsent seitdem und wir alle müssen mit der Zeit gehen.
That's certainly worth $100. Now here's the sphere of Las Vegas. It's $2 billion. It has more impressive, much more impressive holograms. Also, this doesn't quite show you what's going on. But the holograms are really quite spectacular. And the holograms are 2-dimensional objects that have been projected into 3 dimensions. So that's kind of a start. However, it's not impressive enough for what we're going to talk about. So a couple of you may have seen the new 3-body TV programs. This is one of the headsets that's used in the 3-body problem. And when they put these headsets on, it looks really real. I mean, it's like you can walk around on that Earth and it's fine. It's very impressive. Now, the people who reviewed this said it's really magical, but it needs more apps than the one problem they have to solve is, what do you do about the 3-body problem? I'm going to get more complicated, and that's just the idea that the holographic principle tells you that in the space we live, all the information that we see in 3D is actually encoded in 2D. And there's not actually evidence there is a 3D, even though I'm moving up and down, back and forth. The first thing is, there's a nice beautiful theoretical paper that's done a study very carefully, and it's by Juan Maldacena. It's generally known as ADS, anti-de Sitter conformal field theory. And it says if you have a 5-dimensional space with a 4-dimensional boundary, you can show they're exactly equivalent, and that from the 4-dimensional boundary you can reconstruct the 5-dimensional space. Rigorously and nicely proved. This is very different from our idea of what a hologram is. Where a hologram is you take a picture with light that's been split and it's coherent, and you look at the interference and then you reproject it and try and do it. This is, in my way of thinking, an actual different kind of thing, because you don't project it. This is the way it is, right? And it's just, you only construct the other one if you want to. So I have to go through a couple of things. During the time that I was thinking about this problem in other areas, Bekenstein came out with what he called a Bekenstein limit, how much entropy can be put into a fixed region of space. And that Bekenstein limit also happens to be the Bekenstein-Hawking entropy of a black hole. That is, if you try and put more information in a black hole that's already there, it will just make the black hole bigger and make the entropy of the black hole bigger. You can't put more information inside of space than what's in a black hole. And what's in a black hole is the maximum amount of information that can be in that space. And in the Bekenstein limit, it basically says if you have one Planck area on the surface of the black hole, 4 of those makes 1 unit of information. This is a little bit of a sticky point, but it's something that you can go through and derive very carefully. And years ago, I used to teach a course in which I had 3 lectures on the thermodynamics of black holes, and it would derive the entropy and so forth by thinking about advanced society who's got this energy by being a sphere around a black hole, and they generate whatever they need, and they take the waste heat and they lower it down into the black hole and recover as much energy as they can. And there's a limit, otherwise you break thermodynamics. There's a limit, but there's also a limit because the wavelength of the waste heat doesn't fit all the way around the black hole. So you can work out this in different ways. Bekenstein did this in a very clean and nice way. When the idea of the holographic principle came up, there were a set of people who thought, this is great, we can make our universe not from a point in space-time or anything, we can have a black hole collapsing, and then there is a holographic boundary, and that allows us to pop another universe on the other side. And this is not completely bad, but if you look carefully in here, you will see the kind of stuff that we were doing before, and I've done my case, is saying, all right, the universe pops into existence here, and then you have inflation, and you get up to this whole thing. Here, you can do it by having a holographic boundary there, and that protects you from the black hole on the other side, and then you can make the universe on this side. So let me say, the universe neither confirms or denies its holographic nature. There is no super proof either way. There's a lot of circumstantial evidence pointing to the holographic nature of the universe. So one of the things that impressed me at the time is Ted Jacobson wrote a paper in 1995 in which he derived the Einstein field equations from thermodynamics, simply using the law that delta Q is equal to T delta TdS. Now delta, he did a fairly nice presentation, but he had to use what's called a Rentler space in which you have accelerating observers, and the closer you come to the origin, the faster you accelerate. So you end up with hyperbolic orbits. So you get orbits that look like that on either side. And what that does is give you a horizon, which is called a Rentler horizon. And that Rentler horizon has both an entropy flow across it, and a temperature. And when you do that, do the calculations, you see that general relativity drops out of thermodynamics directly. Okay, now this is a shock, to me anyway, because I've been thinking that general relativity wasn't right, that it really should be, basically it looks, when I learned tensor calculus, it looks basically like elasticity theory. I mean, essentially, it's the kind of elasticity theory you would expect if space-time was very stiff, if the space was made up of atoms just the way metal or something else is made up of atoms and electrons, and you bend it and you flex it, you get a nice linear equation, and you get basically this equation. And so, to me, this is a big shock. I'm saying, why should this have to do with thermodynamics? Well, it does and it doesn't, right? Because in order for how general relativity should be, there had to be some substructure. But here, we also know there has to be some substructure. So I'm giving you two examples here. On the left is the Hawking black hole, and it's radiating a temperature, and that temperature is equal to the, Boltzmann constant times the temperature is equal to h times the acceleration of gravity at near the surface of the black hole, divided by c. What Unruh showed some years that Jacobson used was that if you have a vacuum and you're looking at it, it's just empty space, empty of all kinds of stuff. To an inertial observer, it looks like vacuum space. But if you accelerate, you see a uniform temperature. How is it possible that space has a temperature? It's only possible space to have a temperature if it's made of God's substructure. It has to have some degrees of freedom that can be excited and do that. And so this is very similar. The two calculations are very similar. That, again, the Bekenstein-Hawking saying the entropy of a black hole is its area divided by 4, put in array units. What's going on? Well, there's some mass or some energy you've put into the black hole, capital N. There is a horizon around the outside. On this horizon, there are a bunch of bits, represented by zeros and ones here, but it can be more complicated. And it has an entropy from all these bits, and it has a temperature from the Hawking temperature. And that means a mass that's coming to the outside feels a force towards it. And that's a little strange, but that's straightforward. So you can start with this entropy. You can say the change in energy is TdS, right? But the change in energy is just the change in mass times c squared. So you get a relationship that ends up giving you the Einstein equations, both either in the Newtonian form or in the Einstein form. So the claim is, if I have a region of space, I cannot put any more information in it than what a black hole has in that region of space. And that's the maximum amount, but all the information there is on that surface. Well, how do I understand that? Well, I can have two different views. So imagine I'm coming in from the outside, I'm riding on mass m, and I'm going to go in. What happens? When I get to that horizon, information peels off and goes onto a slightly expanded black hole event horizon. Information from me also gets stripped off and goes onto that horizon. And some bulk part of me goes in. There's a two-dimensional part of me that's left behind, and there's a bulk part of me that's left there. This is pretty strange, right? I can get general relativity from this. I can get the fact that the universe is actually two-dimensional instead of three-dimensional. That's a little disturbing. About that time, I was at a visit to IPMU. I was one of the people in Japan, one of the people, and there was a postdoc there, David Eason, and he and I started a project. We got adapted by Paul Frampton, and I was worried, people were worried about the black hole surface, I was worried about the universe surface. So I said, all right, let's calculate what it means for the surface of the universe. Well, the surface of the universe is where all the entropy in the universe is. That's where all the information about the universe is located, is on the surface of the universe. If you look at this, the entropy of the horizon is simply equal to these units from Bekenstein-Hawking, right? You plug all the thing in with the radius of the horizon, the total radius, the overage. You get roughly 10 to the 122 Boltzmann units of information on that. Now, that's pretty much, okay? If you look, I have a plot over here of the time versus the amount of entropy, and you can see the horizon of the universe comes rising up, and then it rises up much more slowly after that. Okay. How is that? What's going on? How come the inflation was important, then the radiation was, but in here are the black holes, and these are the supermassive black holes. They're 18 orders of magnitude or less than the information on the horizon. So we got boundaries, and boundaries inside, but the ones inside are tiny compared to to the overall horizon. So now you can do really simple calculation, same kind of thing that people were doing, saying that Beck-Einstein did. You just say, what's the change in the entropy on the horizon if you change the radius a little bit, because the universe is expanding, right? And you find it's 10 to the 22 delta R over R, right? So that's pretty straightforward. What's the force? It's the change in energy divided by the change in distance with a minus sign, because you're expanding, it's going out. And you find it comes out very simple. It comes out as c to the fourth over g with a minus sign. It's just a pressure. It's a negative force, it's a pressure that's going out. You can then say, well, how much is the pressure for the entropic force? Well, the pressure is just equal to the force over the area. It's just equal to 2/3 of the critical density. What does this mean? Well, at that time, I got excited about this. I said, this makes sense. This explains dark energy. It's all pretty much, when we sent it out to the referees, we got a lot of flack back, but it got published eventually, and it went on listed the same way. At the same time this was going on, there was a proposal by Eric Verlinde that he could explain gravity simply from entropic forces in the holographic principle. Although he didn't have a horizon. Everywhere else that I've done stuff, there's been the Render horizon, there's been the Einstein-de Sitter horizon, there's been the black hole horizon, there's been the universe horizon. All those things, the horizons have an entropy and they have a temperature. This is now just saying, let's put screens up in space and then sum things up. And that gets a little trickier. And you can, in principle, arm wave to get this, but there was a lot of feedback, a lot of flack, and a lot of complaints from him that you can't just choose arbitrary functions, you've got to choose ones that conserve energy, gravitational force that's conserved energy. This, out of that other paper, I got a lot of trouble from the referees about this, that the whole Einstein-Hilbert action is the curvature plus the matter energy in there, plus the surface term. And a lot of relativists don't believe in a surface term, and a few do understand you don't need the interim terms, you can get the surface terms. That is, the surface terms force things to happen the right way. You get dark energy. If you have the right corrections, you can get inflation too. That you can get those, and it's equivalent. The curvature of the surface and the curvature of the bulk give you the same Einstein equations in the end. So that was an interesting thing, but there was not a lot of people jumping on board saying this is a great thing. The thing that's the extreme version of this is the holographic entanglement entropy was going to produce space-time. That is, not only can I get everything for 2 dimensions, but I can get those 2 dimensions otherwise, but it's more complicated. So you've got the Beck-Einstein-Hawking, you've got the ADS CFT, and you got local holography, all that kind of stuff. Then you've got the issue of entanglement and so forth. How can you make it all go together? And the answer is, it's work in progress, but it's not impossible. Okay, so let me answer some of the quiz and then move on to the main part. So the no-cloning theorem is, it's impossible to create an exact copy of an arbitrary unknown quantum state. That is, if I set up a problem and started running my quantum computer and it's gone somewhere, I don't know where it is, I can't make a copy of where it is in the middle, right? So that I can do a checkpoint and run it again if the noise can bother me. And that's a big problem, the noise, what's going on. And so, how do we overcome this, right? Well, it creates a big lot of problems. I'm going to skip on because I'm running late, but I promise the no-cloning theorem proves that you can't teleport a human. And you've got to think about, what does your teleportation system look like? What does it do? Does it mix with the human some random information or not? How does it teleport you? And so forth. And then look and see if you can't make a perfect clone of the entire quantum state of the human being, how can you transport that to some other place? You can do it for an individual particle, but for a human, which is a very complicated set of stuff, you can calculate the error rate, it's extremely high, and you just are not going to be able to clone the person. In fact, I had one that showed a messy person on the other end, but it's sort of not a good taste. But on a broader scale, the no-cutting theorem has big implications for the universe itself, because we're used to, in physics, having a lot of invariance, a lot of conservation laws. We can't afford to have some quantum information destroyed. It's a big problem. Information being destroyed is a really big problem. It causes us to lose, a lot of the laws that we consider basic laws of physics. How do we deal with this? Well, about the same time some of this other stuff was going on, quantum computing had a breakthrough, and they realized they can do ground-breaking error correction. So in 1995, Peter Shor introduced a way to do quantum error correcting. And his method was to take your ordinary logic bits, or your physical bits that are in your cloning system, and quantum entangle some of those in groups so that you can then check and see what's going on. And if you implement it properly, you can arbitrarily reduce it. Now, the issue is going to be, it requires you have a lot of extra supercomputing bits in order to do this. It takes up part of your resources. Here's an example of what's called a surface mode. And this one is done for two kinds of errors, the phase flip errors and the bit flip errors. These are your individual physical quantum bits, right, in your quantum computer. And you associate in an entangled system, these guys all outlined in blue. And now, one of your guys goes bad, right? Why does that happen? Well, it turns out you need to be running your quantum computer. It's going to be, there's a certain bit error rate that happens, and you're going to make this. Bits are going to flip. And here, you can tell these two guys are associated, or those two guys are associated. They give you a hint that there's a quantum error. And if you had sufficient number of these, you could go in and correct that and have it continue on with the calculation. And this is the trick in the quantum correcting errors. They're trying to link many bits. Now, if you're a company, Google or IBM or so, and you're trying to do it, you don't want to have to use a lot of bits. You want to find the most efficient way of correcting the errors and seeing how they go on. But if you're the universe, how many bits do you want to have to make sure that you don't violate baryon number, or you don't violate charge conservation or momentum conservation, or whatever it is? It depends on how complicated you're making things. Here's an example. We know that for the black hole surface, there's one bit of every information for every 0.7 times 10 to the minus 65 square centimeters. That's a lot of bits. A black hole that's just as big as, 10 kilometers across, that's a lot of bits, right? That's the 1022 for our horizon. And so you can think about, how do you set that up? The first pictures that people drew look like this, and then people started getting fancier and making pictures that look like this. And then people started realizing that if you tile space with non-repeating patterns, like this or like this, you have many more possible ways to entangle things. So that you can do a number of things. You can do topological ones, you can put them on a torus, or you can put them on these non-repeating tiles. And then you can make a very large number of bits that are separately entangled, and therefore you can keep track of where potential errors might be, or reduce the chances of there being errors. We need to have a conformal transformation. Here's the simplest conformal transformation I could find. This is a little square with squares in it, made into a bigger square with squares in it. Conformal usually keeps the angles constantly. But this is pretty simple. These guys are conformally related to each other. But you can think about the AD-CFT. Here these guys are conformal. This is in the infrared region, where it's very long, big scale. And here is the ultraviolet region, where it's a small scale. And you can say, how does this work? Well, if I have a conformal interaction, if I have a pattern here, and a pattern here, or a pattern there, they're different sizes. How much they overlap and how they do it tells us how close they are together. So that I could just have a simple square like this, and effectively have a third dimension encoded on that square, just based on how big my quantum bit calculations are. That is, imagine I brought in a big flat square or a big balloon, and it had a huge number of pixels in it, And then I can put patterns in of very different sizes, right? And the big guys they're far away from the little guys because their interaction with them, they don't overlap as much, their interaction is small. So there's a segregation, which isn't a physical segregation, but is a coordinate segregation, that you don't actually have to separate them out. That is a way you could make a universe that's two-dimensional seem to be three-dimensional. And that's the thing you can do in quantum computing too. The other thing that you can do, you can think about it this way. Imagine you have the black hole on the outer surface. The one you think is furthest out on the black hole at the horizon has Planck size, four Planck size little bits. And then I make patterns that are much bigger. Well, they're effectively look like they're further in, right? You see how the squares get bigger. So I can do that. I don't have to make it with these little squares. I can use, there's many different ways I can tile the surface, so I can do this in a lot of different kinds. So it looks like I have nested spheres to the people who are living on the two-dimensional surface and looking from the outside, but I just have a two-dimensional surface. How is it that I got this two-dimensional surface out here, but I got all those, billions of galaxies in there? Well, that's a problem for the student. My conclusions are, an ideal quantum computer would really have a lot of the properties of the universe, and the universe has the properties of an ideal quantum computer. It's about as ideal a quantum computer as you can imagine. So the question is, which side of the question is the right side of the question? Or are they both the right side of the question? Thank you.